We dealt with yield surfaces. Now let's deal with the direction of plastic flow. We usually call this as flow rule. If you remember, we noted that for most metals, the direction of plastic flow is in the same direction as the applied shear stress. We borrowed this idea from incompressible fluids, where the flow occurs along the as a shear in the fluids. Also, we started the yield function with it being a simple function of J2. Supposing we find out the derivative of J2, it gives you derivative of J2 with respect to stress, it gives you shear stress. We also borrowed an idea from the flow net, which defines the direction of flow and the potential lines, which are perpendicular to each other, and we use this fact that the flow occurs normal to the potential lines. This is called normality rule. So combining all this, we came up with an idea that we could perhaps use yield functions as potential functions, so that the derivative of the potential function, which is nothing but the gradient of the potential function, is the direction of flow. Or in other words, the flow is occurring normal to the yield surface. This is popularly known as associated flow rule. Flow rule that is associated with yield function as a potential function. But now, recently, we have introduced yield surfaces other than those that depended only on shear stress. Or in other words, we have a scenario where normal stresses could play a role in the direction of plastic flow. But this flow need not be normal to the yield surface, because there is volume change that contributes to plastic flow or plastic deformation. Therefore, yield function may not be the ideal function to choose for potential function that we use for finding the direction of plastic flow. So if I have a plastic potential, the normal to it is the direction of the flow. And therefore, we now introduce a plastic potential function in addition to yield function. Yield function defines the point of yield, while potential functions define the plastic flow direction, which are normal to the plastic potential. These flow rules that pertain to plastic potential are called non-associated flow rules. We'll use this concept in order to write down the equations. And therefore, the plastic potential, we assume the plastic potential to be a scalar function H as a function of sigma, plastic strain, and certain internal variables. One of the internal variables that we already know is the isotropic hardening parameter, right? There are several internal parameters that can be introduced in order to explain the events that occur, the way in which the material behaves. So, we assume that there exists a scalar function H, which is a function of sigma, stress, plastic strain, and a set of internal variables Q. Okay. Some of the internal variables that we know are isotropic hardening parameter, kinematic hardening parameter, and so on. Okay. They explain what the change is that has occurred internally in the material. Okay. And as we stated earlier, the plastic flow, which is defined by epsilon dot P, is proportional to the gradient of the potential. Okay. This is called the, in fact, this is non-associated flow rule. It is an associated flow rule when it is a special case where H is replaced with yield function. And therefore, this is more of a general flow rule. Instead of calling it as non-associated flow rule, I would call it as a general flow rule. And when H becomes F, which is the yield function, it is an associated flow rule. Now, if I add that into the set of constitutive equations that we already know, then we have the elastic equations given by this. Yield condition given by f of, I'm going to introduce a psi here. Psi is nothing but sigma minus alpha. Alpha, as you know, is the back stress. So I can write the yield function in terms of that divided by k minus 1 equal to 0. Okay. And then the flow rule, where P is nothing but the gradient of plastic potential with respect to stress. Okay. Here we have also added kappa, which is the isotropic parameter. And then the contact condition. So this entire thing, set of equations, define how the material behaves if non-associated flow rule is applied. They're called non-associative materials. And if we derive, just like what we have done earlier, in order to find out the relationship between the change in stress to change in strain, these two are tensors right now. And this K is the tangent stiffness matrix. That will happen to be the elastic modulus times I minus H, which is a hardening value, times P dyadic C N, where N is dou F by dou sigma, P is dou H by dou sigma. As you can see here, this portion is not a symmetric portion unless I have an N over here. Okay, so in that sense, I will obtain a tangent stiffness matrix which is unsymmetric unless H is equal to F. For example, in Drucker-Power model, which is used for granular materials, we have a yield function in this form, where T of Q comma R, if you remember, Q and R are the two parameters which are related to the shear stress minus the pressure times tan beta, which is the shear angle, friction angle, minus some constant is equal to 0. Okay, so this is a modified form of what I had written earlier. Okay. PQR are nothing but the stress invariance introduced. Earlier we took this as J2. Okay. For this, since it's a friction type of material, we introduce a plastic potential. Okay. Don't ask me why this kind of a plastic potential. Assume that this is the plastic potential that I have assumed. With this assumption, it is possible for me to find out the plastic flow rule, which is nothing but the derivative of H with respect to sigma times phi, right? Which also can be written as the one that is attributed to shear part and the dilatational part, by appropriately taking the derivative with respect to shear and pressure. So I'll get these two, and I can introduce these two into my equation. And therefore, the core elements of the elastoplastic model or a list of state variables S, which are these: sigma, strain, plastic strain, kappa, alpha, and so on. These will form the internal variables or inelastic variables called Q. There are three scalar functions: the strain energy function that we already know, the yield function, and the plastic potential. There are three of them that are defined. Then the stress response can be written very simply as the derivative of the stress as the derivative of epsilon, the flow direction as along the derivative of plastic potential with respect to reduced stress, sigma minus alpha, and the Kuntaker condition. Okay. We also have to introduce how alpha is going to vary and how kappa is going to vary. Okay. So all those variables have to be shown to be how they are varying. The evolution of these variables Q should be specified with respect to time. Okay. This is basically what we need to do in order to define the constitutive equations. Just borrowing whatever ideas that we already had in one dimensions, isotropic hardening kappa dot can be written this way. We wrote in a very similar way as this, right? In this function is the function that you choose appropriate to what you observe in the real material. Okay. So if I use these connections, for example, S is nothing but this integrated over time. And if I multiply kappa with respect to S dot, I'll get phi, which is nothing but the plastic rate of plastic work. S dot can be now found out to be nothing but psi times dou F by dou kappa, and S dot is equal to phi by kappa. These can be derived. And therefore, I get an equation which is like this. Okay. The choice of this function could be any one of them. We looked at some of those choices earlier. One is called linear hardening, Swift law, and Gauss's law. Similarly, kinematic hardening, compared to isotropic hardening, which is a scalar parameter, kinematic hardening is alpha, which has the same dimension as stress, can be written in many ways. The simplest one was proposed by Prager, later changed to Ziegler in order to use for subspaces, where alpha dot is taken to be proportional to the way in which the plastic flow occurs. Armstrong and Frederick modified it, stating that there is some aspect of alpha that contributes to how alpha is varying, and therefore introduced another term over here, which is dependent on the current alpha. We call it as pre-stress, right? So it has a pre-stress effect that it sees as it evolves. Okay. Of course, if you look at it carefully, I have an S dot, which is nothing but the absolute value of epsilon dot plastic, and epsilon dot p, which means that epsilon dot p is seen as common in these. I can take it out and write it as 5 times a function. This function gives normal over here, dou F by dou sigma, as you can see, and the other one as C2 by kappa. Okay, phi by kappa is what we got. If I take the phi out, then C2 times alpha by kappa. Okay, so this is another form that we can write. So now putting all of them together, and this is for a quadratic functional. We have the elastic constitutive equation as we have already looked at. The yield function, I've written it like this, is a very generalized function where y is the parameter for the material. divided by kappa square minus 1 is equal to 0. This is a very general, but a quadratic type of yield function that is being defined. And then, of course, the flow rule. This gets modified if I have a plastic potential. Else, I will get it to be something like this. And then you have the plastic arc length, S dot, that we have already seen as something that changes kappa. As kappa dot is equal to this, together with Grundtagel conditions, where it tells you when the plastic flow is occurring. So if I take all this and write down as equations, I'll get 20 different equations. These 20 differential equations will be in terms of sigma, epsilon, alpha, kappa, and S. You'll notice the dependency of plastic strain has been removed here. You can either specify how the stress is varying or the strain is varying. So if you look at this, you have a 6 plus 6 plus 6, 18 plus 2, 20 unknowns. If I introduce also the variation of one of them as a specification. With these 20 differential equations, which are a system of equations, first it is possible for me to use OD 45 or 23 in my MATLAB code in order to solve the problem. This is as simple as that. Hope things have been clear here. We have moved from a one-dimensional to a three-dimensional. We looked at yield surfaces. We looked at the equations that we obtained for a three-dimensional scenario. And now we are solving the differential equation, the state equations that we get, but with 20 different unknowns to be solved for. Okay. If you look at my book, we have solved a couple of scenarios for a particular material. I want you to go through that and understand it. Now coming to the assignment. What do I need from you as a term project? I want you to choose, just like what you did earlier for one dimension. I want you to choose an appropriate material. Even if it is simple, it's okay. Define all these things. I want you to simulate for certain loading conditions and submit it as a report consisting of output from the code that you have written for this. I hope it's clear. This is a term project, a modified term project that I'm giving you right now. You can use MATLAB, you can use any other software, it does not matter. But it essentially is solving the 20 differential equations with 20 unknowns with a specification within this of either stress variation or strain variation, or probably a combined one. Thank you.